Welcome to Math 252, Section 15.6 on tangent planes and linear approximations. On the first page of this notes, we're going to cover a bit of review that will help us get ready to understand the heart of the lesson. Generally speaking, we have been working with functions of two independent variables written explicitly in the form z equals f of xy. It's often convenient, though, instead to write this in implicit form as some capital F of xyz equals 0. Both of these forms represent a surface. In the second form, it represents a specific level surface for some function w equals f of xyz, the one for which w equals 0. So let's just quickly review what a level surface is. Example 1. For the function given by f of xyz equals 4x squared plus 4y squared plus 4z squared minus 36, describe the level surface given by capital F of xyz equals 0. All right, we're just going to set that function, 4x squared plus 4y squared plus 4z squared minus 36 equal to 0. We can move the 36 to the other side, and we can divide everything by 4. Do you recognize what type of surface this is? Yep, you got it. This is a sphere centered at the origin with a radius of 3. Example 2. For this function, describe the level surface given by capital F equals 0. So again, let's take our equation and set it equal to 0. Let's move the 12 to the other side and see if we recognize what type of surface this represents. Do you recognize it? Great, you got it. This is a plane, since neither the x nor the y nor the z are squared. All right, a bit more review before we get to the new material. Back in Chapter 13, we learned to write the equation of a plane. If we know the plane contains the point x naught, y naught, z naught, and we know that the normal to the plane is the vector a, b, c, then the equation of the plane can be written a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, or more generally, can be written ax plus by plus cz equals d. Okay, the last piece of review that we need before we can get to the heart of this lesson is to remember the equation of a line. Given that your line contains a point, x naught, y naught, z naught, and you have a direction vector for the line, then the vector equation of the line is given by r of t equals the position vector for the point, x naught, y naught, z naught, plus t times the direction vector abc. All right, that's all the review we need. Now we're ready to learn today's lesson. Let's go to the next page. In 2 dimensions, when we have a curve, we talk about the equation of a tangent line. But now here in space, we have a surface. So what we want to look at is the equation of a tangent plane to that surface. Let's go through the derivation for the equation of the tangent plane. Suppose you're given some curve, C, noted in the picture by the green lines, where that curve is a curve that lies on the surface. Notice there would be an infinite number of these, and that curve is passing through a particular point, p sub 0. The surface is going to be given by an equation, capital F of xyz equals 0. Okay, number 1, let's write out what the derivative of that capital F function with respect to t would be using the chain rule. From our work with the chain rule, we know that df dt would be the partial of f with respect to x times dx dt, plus the partial of f with respect to y times dy dt, plus the partial of f with respect to z times dz dt. And since that capital F equaled 0, then this derivative would also equal 0. Now, given the vector equation of the curve, r, we can find the equation for r prime of t. And r prime of t would simply be the vector given by dx dt, dy dt, and dz dt. We could also write the vector for the gradient of our capital F function. And the gradient of f would be the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. Now look carefully again at what we obtained when we found df dt using the chain rule. Look carefully at the products that you see and the fact that we're adding those products together. Does that make you think of any kind of topic that we learned with regard to vectors? You're right, that's a dot product that we see. In fact, what we can see is that the dot product of the gradient of f and the r prime of t vector is 0. And remember that the r prime of t vector would be a tangent vector. Well, if the gradient dotted with the tangent vector is equal to 0, then we know that that gradient is in fact orthogonal to that tangent vector. This is important because we know that in the equation of a plane, the coefficients a, b, and c have to represent a vector orthogonal to a plane. And we now know that the gradient is in fact orthogonal to the tangent vectors to the surface. Okay, let's go on with some definitions. Let f be a differentiable function at some point p on the surface S, where the surface is given by capital F of x, y, z equals 0, and the gradient of f is not the 0 vector. Then number 1, the plane through that point that is normal to the gradient is called the tangent plane. Or another way to say it is that the gradient is orthogonal or normal to the tangent plane. And the line through that point having the direction of the gradient is called the normal line to the surface. Let's give even more specifics about the equation of that tangent plane then. If f is a differentiable function at a point x naught, y naught, z naught, then an equation of the tangent plane to the surface given implicitly by capital F of x, y, z equals 0 at that point is what? Well, first of all, remember, how would we express the gradient? The gradient of f would be expressed by the partials. Partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. And we know that the gradient represents a normal vector to that plane. Well, on the previous page, we just reviewed how to come up with the equation of a plane. And we know that the coefficients in that equation are in fact the components of the normal vector. So here we go. Here is the equation of the tangent plane. The equation of the tangent plane will be the partial of f with respect to x times x minus x naught plus partial of f with respect to y times y minus y naught plus partial of f with respect to z times z minus z naught equals 0. Now, by the way, those partials, the partial of f with respect to x, etc., all need to be evaluated at the given point. You need numerical coefficients there. Now, that was if we had written the surface implicitly with that capital F of x, y, z equals 0. If instead the surface is written explicitly as z equals f of x, y, then what would the equation of the tangent plane be? Well, note, if we have it written in the form z equals f of x, y, we could subtract the z over and have 0 equals f of x, y minus z, which means the partial of that equation with respect to z would be negative 1. We also have that z naught would simply be the point. In addition, the z naught value is simply the z value of that little f function. It's the f of x naught, y naught. So if you work a little bit with the equation we've already written and solve for z, you obtain the following. Z, and I use z sub t for the z representing the tangent plane, is the partial of f with respect to x times x minus x naught plus the partial of f with respect to y times y minus y naught plus f of x naught, y naught. That's just your z value at that point. And finally, what's the equation of the normal line at P? Well, remember on the previous page, we just reviewed the vector equation of a line. We know it passes through the point x naught, y naught, z naught, and we know the direction vector would be partial of f with respect to x, with respect to y, and with respect to z. So our equation, r of t equals the position vector x naught, y naught, z naught, plus t times the direction vector partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. All right, let's go on and look at some examples. Example 3. Find the equation of the tangent plane and normal line at the point negative 2, 1, negative 3 to the ellipsoid given by the equation x squared over 4 plus y squared plus z squared over 9 equals 3. All right, our first thing is to rewrite this equation with that capital F of x, y, z equal to 0. Once we've done that, we can do the work required to answer the question. The first part of the question asks us to find the equation of the tangent plane to this ellipsoid. To find the equation of the tangent plane, we first need the components of the gradient, because we're going to need our partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z. Fortunately, with this equation, those are pretty easy to find. So our gradient of f is given by the vector x over 2, 2y, and 2z over 9. Now we need to evaluate that gradient at the given point. So go ahead and evaluate the gradient at the point -2, 1, -3. Write that down. Okay, do you have the same thing I have? It's the vector -1, 2, -2/3. All right, then we have everything we need to write the equation of the plane. We simply use the components of the gradient as our coefficients for our plane. So here we go. The equation of the plane is -1 times x plus 2 times y minus 1 minus 2/3 times z plus 3 equals 0. Now we could go further and clean that up, but if I haven't given you any specifics about the form of the equation of the plane, then we'll just keep it where it is. All right, the second part of the question is to find the normal line. Well, we already have all the information we need for that. All we need is the position vector for a point and the direction vector, which is the same vector we used to obtain the coefficients of our plane. So the equation of the normal line is r of t equals the vector -2, 1, -3 plus t times the vector -1, 2, -2/3. All right, before we go on to the next example, let's take a look at what we just figured out. Let's take a look at the graph in 3 dimensions of the ellipsoid and the tangent plane at this particular point. Using GeoGebra, I've graphed the ellipsoid and I've graphed the tangent plane. If I pull it around a little bit, you can see that plane is tangent at the given point, which I labeled A. So we have our ellipsoid and we have our tangent plane. All right, so GeoGebra is a great little tool for just kind of checking your work and seeing what this actually looks like in the real world. Let's go on now to example 4. In example 4, we're given the surface in the form z equals. So we actually have 2 different ways we could approach this. Method 1. We could rewrite this as a capital F of x, y, z by subtracting the z over to the right-hand side and setting this equal to 0. If we do that, then we're going to start with the gradient of our capital F. The gradient of f would be the vector -2x, -y over 2, -1. Then we need to evaluate that at our given point. And so evaluating the gradient at the point 1, 0, 8, we get -2, 0, -1. Now writing the equation of the tangent plane, just like we did in the previous example, we have -2 times x minus 1 plus 0 times y minus 0 minus 1 times z minus 8 equals 0. We'll clean that up just a bit by distributing and combining like terms and all of that to obtain the equation of our plane, -2x plus 10 equals z. Now the other option would have been to leave it in the form z equals. So method 2, leave it in the form z equals and use the second form that I showed you for the equation of the tangent plane. Again, we need to start by obtaining our partials. Our partial of f with respect to x is -2x, and our partial of f with respect to y is -y over 2. Those form the components of a gradient, and we need to evaluate that at the point 1, 0. So the gradient of this little f at the point 1, 0 would be -2, 0. Now we write the equation of the tangent plane. Z sub t, for the z on the tangent plane, equals -2 times x minus 1 plus 0 times y minus 0 plus whatever z equals when x is -2 and y is 0. And we already know that from the setup of the problem. That's 8. Now if we work this one out, cleaning it up a little bit, lo and behold, we get the exact same equation that we got when we did it using the other method, which of course we better, or we've made a mistake, a grave mistake. All right, we've now practiced this same idea twice, so I would like you to go on and try example 5 on your own. When I post the completed notes in Canvas, example 5 will be worked out, but you try it on your own and see if you're able to work through the problem and get the same answer I got. This will be the end of part 1 of your section 15.6 notes. after you've worked out example 5 and you're ready, go on to the video part 2.